Okay, here we are with the second part of the Chapter 3 textbook problems, and if you're only looking at this chapter, if you didn't look at the earlier Chapter 3 problems, that's fine. You may have found that those were easy. If not, then I would direct you back to looking at those worked problems first before you start here. So I'm going to do a selection of problems from our textbook. I'm in the 6th edition this time. I'm in Chapter 3, the end of chapter problems, and I'm going to be looking at section 3.6, 3.7, and 3.8. I'm not going to do every problem, but I'm going to do a couple of them to give you sort of just another resource to work with in helping you to understand the material before you take the quiz and before you do the homework, actually. So I'm going to, in terms of like sort of orienting yourself, I'm going to do number 70. So I may have to come back to the slide to remind myself of what you're doing. But this might be an opportunity for you to stop, do all these problems or do some of them, and then come back, watch me work through them, and then maybe go off and do some more or whatever. But that sort of gives you an idea of where we're going and how many we're going to do. So I do not recommend just watching me do this. That's not going to be an effective learning technique. You need to actually attempt the problem on your own first and try and figure it out and get stuck and get messy and then come back and say, okay, now I have a better understanding of what I don't understand. And so then you can watch the solution, and that will help you sort of pinpoint your issues. Versus if you just watch me do it, you're going to have this false sense of understanding that is coming from the fact that I know how to do the problem and not from the fact that you do. So make sure you stop the video and then actually do the problems yourself. So here's number 70. It says, the following statements define or are closely related to the terms electron shell, electron subshell, and electron orbital. Match each statement with the appropriate term. So we have electron shell, subshell, orbital, and just those three. Okay? So remember, before we get started on this question, remember that if we were talking about a house, let's draw a house. It's going to be kind of a funny shaped house. We would say that the floors of the house were equal to the shell. And then there might be a really, really long room, and there might be a really, really small room. Excuse me, a really, really small apartment. And so the shape of the apartment on a particular floor, that would be my subshell. And then within any particular apartment, I might have some number of rooms. So I might have this room here, and this room here, and this room here in this apartment. And so the number of rooms, we know, is equal to the number of orbitals. Okay? So let's make sure we're just all fresh on what those concepts are. All right. Now, looking at the problem. This unit can contain as many electrons as or more electrons than either of the other two. Well, if we think about our house, the shell can definitely contain more electrons than everybody else. So the answer to A is shell. B, the term energy sublevel is closely associated with this unit. But that whole sub term is kind of a giveaway. This is the subshell. C says electrons that occupy this unit do not need to have identical energies. Ah, now we get into some interesting things here. That would be different shells. Because if you're in the same orbital, you're at the same energy, and if you're in the same subshell, you're in the same energy. Just like your room is all the different rooms in the apartment are all on the same floor. Just like all these apartments are on this floor. Versus if I'm on this floor and this floor, those are clearly different amounts of energy. D says this unit is designated in the same way as the orbitals contained within it. That is a subshell. So we might talk about a 2p subshell, or we might talk about one of the 2p orbitals in the 2p subshell. 72 says, indicate whether each of the following statements is true or false. All the subshells in a shell have the same energy. That's true. B says, an s orbital has a shape that resembles a four-leaf clover. That's false. S orbitals are sphere shapes. That's your s orbital shape. Oops, I need to go on to C, not another B. 72C says the third shell can accommodate a maximum number of 18 electrons. So the third shell, that's going to have the 3s, the 3p, and the 3d subshells in it. And the 3s has one orbital, the 3p has 3 orbitals, and the 3d has 5 orbitals. And each of those has 2 electrons. So there are 2 electrons in the 3s, 6 electrons in the 3p, and 10 electrons in the 3d. And if we add those up, that's 18 electrons. So letter C is true. D says all orbitals accommodate the same number of electrons. That's true. All orbitals can take up to 2 electrons. So D is true. Number 74. Give the maximum number of electrons that can occupy each of the following electron accommodating units. A says one of the orbitals in the 4D subshell. Well, we don't actually have to get too excited about the 4D subshell piece because it says only one of the orbitals. And we know an orbital can only take 2 electrons. So one of the orbitals in the 4D subshell can only take up to 2 electrons. And the same goes for letter B, one of the orbitals in the 5s subshell. Again, we're just talking about a single orbital, so only a maximum of 2 electrons. C is where things get interesting because we're talking about the 3D subshell. And we know that the 3D subshell, as any D subshell, has 5 orbitals. And we know that each orbital has 2 electrons. So we know that the 3D subshell can take up to 10 electrons. For letter D, we're talking about the second shell. And so now we have to consider who's in the second shell. Well, the 2s subshell is in the second shell, and the 2p subshell is in the second shell. And we know that the 2s has one orbital, each of which takes 2 electrons, so that's 2 electrons. And the p subshell has 3 orbitals, each of which take 2 electrons, so that gives me 6. And I have 2 over here for a grand total of 8 electrons. Should be your answer to D. All right, now we're going to go on to 76D. So 76D says write complete electron configurations for atoms of each of the following elements. And D is titanium. And so I find titanium on my periodic table, and I recognize that I have to place all 22 electrons in the appropriate subshells. So every electron configuration starts out the same way because all electrons start in the same first subshells. So the first subshell is always 1s. There are 2 electrons there, so I pop that 2 right up there. My next subshell, because I'm finished with the first row of the periodic table, now I'm going down to the second row. I'm in the s block. It's 2s. There are 2 boxes of elements on the periodic table, lithium and beryllium, that are in the 2s, and so that's 2 electrons. I'm still in the second row, though, because I haven't finished it. I still have the 2 p's, and that goes from boron, carbon, nitrogen, oxygen, fluorine, and neon. So that's 6 boxes, so that makes me 2p6. At this point, I'm at neon, so I'm finished with the second row, and I need to go to my next element, which is sodium, which is in the third row of the periodic table. Third row means I'm now in the third energy level, and I'm in the s, and there are 2 electrons because there's 2 boxes there. Keep going across to the P's, starting with aluminum and ending with argon. 6 boxes, so 3p6. I'm done with the third row, so I come on down to the fourth row. I see 4s2, and then something interesting happens. Between calcium and scantium, element 20 and element 21, I move from the s subshell region of the periodic table to the d block. And we know that in the d block, the energy level is the row number -1. So I'm in the fourth row, but these d electrons are in the 3ds. And so I'm going to count over to titanium, 1, 2 boxes, and so therefore I end in 3d2. Okay, let's go on. I got to flip back here to chapter 3. So we just did 76D, and I don't remember what else we're doing. So let's go back. 88AB, 90. Whoops. I'm going to write this down so I don't have to complete. 88A and B, 90, 92AB, 94AB. The things you learn as you go through this. Okay, so 88AB, so 88A first, says write electron configurations for the following elements. The group 7A element in the same period as magnesium. So we're looking for magnesium is in the third period, and group 88A, group 7A is going to be the halogen, which is chlorine. So I need an electron configuration for chlorine. So it's 1s2, 2s2, 2p6, 3s2, 3p5, because I am 5 blocks into the chlorine in the 3p's. On B, 88B, we are looking at the second period element in the same group as tin. So second row, tin is in group 4A, so I'm looking for carbon's electron configuration, which is 1s2, 2s2, 2p2, and I'm done. Okay, number 90. Referring only to the periodic table, determine the element of lowest atomic number whose electron configurations contain each of the following. Only to the periodic table. So we're looking for elements with the lowest atomic number. So the first element for which this is true, whose electron configuration contains 2 completely filled shells. So 2 completely filled shells would be shell number 1 and number 2. So 1s2, 2s2, 2p6, that would be a completely full first shell and a completely full second shell. Now the question is, who ends in 2p6? Well, there's 2 ways I can approach this. I can count up my electrons and say, oh, 10 electrons. For a neutral atom, that would also mean 10 protons. And so I could go to the atomic number and find 10 electrons, that's neon. Or I could go to my periodic table, find the second row, find the p block, and go to the end of the p block. And that's neon as well. So 90B says 2 completely filled subshells. So we have 1s2, that's 1 subshell. And then we're looking for our second filled subshell, which is just going to be 2s2. So 1s2, 2s2, who's 2s2? That would be beryllium. Letter C, 2 completely filled orbitals. That's also going to be beryllium because the 1s and the 2s both only have 1 orbital. For letter D, 2 completely filled p subshells. So I'm looking for 2 p subshells that are totally full. So 1s2, 2s2, 2p6. There's my first completely full p subshell, but I need another one. So now I go 3s2, 3p6. There's my second one. Now who is that? Well, I go to the third row, to the end of the p block, because that would be p6, and I find that it's argon. All right, 92, A and B. So 92, A, says indicate whether the elements represented by the given pairs of electron configurations have similar chemical properties. All right, so what we have to remember here is that in order to have a similar chemical property, you have to be in the same column of the periodic table. So what we also know is that elements that are in the same column end with the same type of subshell and the number of electrons in that subshell. So when we look at A, it says 1s2, 2s2, 2p4 versus 1s2, 2s2, 2p5. So right there, I've got an issue. This one ends in 2p4. This one ends in 2p5. The p4 column would be 1, 2, 3, 4. That would be oxygen. And the p5 would be fluorine. So clearly these are not the same element. So they don't, excuse me, they don't have to be the same element. They have to have the same number of electrons in their final subshell. So the fact that I have a p4 here and a p5 tells me they are not in the same column of the periodic table, and so they don't share chemical properties. Let's do B. It says 1s2, 2s2, 2p6. No, let me go back to black. 1s2, 2s2, 2p6 versus, am I doing 92? Nope. I tried to do 91 there for a moment. I could just ignore that. So 92b says 1s2, 2s2. And the other thing that I'm looking at is 1s2, 2s2, 2p2. Okay, so where are the S2s? Those are my alkaline earth metals. That's the second column of the periodic table. Where are my P2s? Well, that's group 4A. So these guys are definitely not in the same column of the periodic table, and so they don't share chemical properties. Let's see if we can find one that does. Actually, in our next one, in C, you can see we have 1s2, 2s1 versus 1s2, 2s2, 2p6, 3s2, 3p6, 4s1. And notice here, I've got an S1 and an S1. So both of those are in the same column of the periodic table, so they share chemical properties. Okay, let's look at 94A and B. So specify the location of each of the following elements in the periodic table in terms of S area, P area, D area, or F area. So in A, we're looking at aluminum, which is element 13, and that's definitely in the P block. In B, we're looking at potassium, which is element 19. That's in the first two columns. Potassium is actually in the first column, but the first two columns are the S block of the periodic table, so potassium is definitely in the S block. Okay, that concludes this video.